Day one. We're going to be looking today about inference about regression. So these inferences are going to be specifically about slope. We have some conditions. And they're a little different than what we've been used to. Let me get to my book here real quick. Where did that disappear to? It's in there somewhere. All right, so the conditions are, is it linear? If it's not linear, you can't make any inference about it. How do we know if it's linear? Well, is R greater than the absolute value of 0.7? Is R squared greater than or equal to 0.5? Those are two ways. Or, and maybe, no pattern in the residuals, right? Is the residual a scatter? All right, the next one is it independent? The independent calculation that we're used to is the 10% rule, but this one's a little different. Would the data sources be independent? I mean, literally, is there a connection between them? It's been a while since we've talked about stuff like that, but if you remember when we talked about collecting data, if I were to ask each of you individually, let's say, hey, what's your favorite car company? You probably wouldn't feel any pressure to say anything other than what your favorite is. But if I asked you collectively, hey, what's your favorite car company? And there's some jerk in the back going, Chevy, man, it's Chevy. Chevys are the best. Chevys will always be the best. They've always been the best. It's Chevy. And the rest of you might go like, yeah, what a jerk. I'm going to say something else even if I think it's Chevy. Or you might go, I'm just going to say Chevy so the jerk in the back shuts up, right? So if there's some bias, then that hampers your independence. So we're trying to see if we think that things are independent. Is it normal? All right, I'm going to give you the book definition of normal for this. For any fixed value of x, your input, the response y follows a normal pattern. have to say is if I understand this the way it's written, and I think I do, yikes. So if you have a big set of data, you'd have to look and see if all of the outputs for every input follows a normal pattern. The book gives a picture of that idea here. And I don't even know where I'd begin to kind of try to verify that. I think it would be a nightmare. It would be a nightmare. So how do we do it? Well, we're going to graph the histogram. Of x and the residuals of y. So, the histogram graph of your residuals, if it's roughly normal, approximately normal, or just doesn't have any outliers or large skew, because we'll be looking at t-values here, you're good. Because this is ridiculous. All right, next one is equal SD. This is one we haven't seen before either. And that's the standard deviation, or call it sigma, is the same for all values of x. Standard deviation of y is the same for all values of x. Now, this one can be seen visually in the residual plot. If I were to draw a residual where the standard deviations were the same, it would look kind of like this. Let's see. Where roughly the distances on top and the distances on bottom are the same. Okay? Where it would be a problem for this would be if I had something that looked like this. Because the distance away from the residual line on average is the same for the points below the line as they are above the line, but there are more points below the line and they're closer to it. So that causes a problem, and that's where your equal standard deviations fall apart. So you've got more points below, and it's not evenly distributed. Okay, so that's the way you can look at the residuals for that. And the last one, is it random? Some randomness has to occur in the problem. We're going to see a problem today where it's going to be talking about blood alcohol content. And so they took some number of volunteers would volunteers be random? No. They took some number of volunteers and they had them drink beer. And how did they randomize it? Well, they randomly selected how many beers a person was supposed to drink. So you got some, I don't know, pull a number out of a hat or something like that. We'll look at that problem here in a second. So all this leads us to regression. The regression equation, well actually this is review. The regression equation that we're familiar with is y. This is how it's given in the calculator, but we know it to be y hat equals a plus bx, where a is the y-intercept and b is the slope. So y hat is our predicted value. A is our y-intercept. But we have a new value for that as well. This is called beta. It's kind of a fancy b. B sub naught. And also little b sub naught. They don't use b sub naught in the calculator, so you have to know that these guys are the y-intercept, the a. The b is the slope, which is beta sub 1, or b sub 1. And of course the last thing, the x, is just your input value. That doesn't change. So why do you think we have big B and little b? What if we learned in this class that has used the same letter but as a capital and as a lowercase? What's the difference between the capitals and the lowercase? Yep, population versus statistic. So these guys are going to be your population values. These are your statistic values. Now, looking at some of the stuff that I've seen in this book and in other books, there's probably some pattern to it that I haven't caught on to, but it seems like they willy-nilly use one versus the other. Like they'll switch B sub 0 and B sub and beta sub 0 and stuff like that. I'm sure they don't. That's just what it seemed like to me, but that's what we've got here. We've got population and statistic, or sample values. All right, and that leads us to a confidence interval. The confidence interval formula here is dealing specifically with the slope. It's beta, or small beta, sub 1, plus or minus t star, times SE, that's standard error of the slope, b sub 1. It looks different, but it's really not. It's the same as all the others that we've done. We're just using now slope instead of mu or x bar. Actually, I never use mu, x bar or p hat, right? And nothing's changed. We're still looking at 90, 95, and 99% for Skittles, law, and life and death. And this is inference about a slope, about the true slope inference about the true slope of the line of regression. What is the true slope? That's going to be your beta sub 1. So we are 99% confident that the true slope of the line of regression for context here is between this and that. All right, almost done with the notes. Let them sleep. If somebody wants to sleep through my class, they can sleep through my class. Calvin, be nice. That was peer pressure? So you're blaming it on Riley again? Well, that's actually more believable. All right. Test. Anytime we have a test, at least anytime lately, we're looking for a null hypothesis and an alternative hypothesis, right? The null hypothesis is always something is equal, or something is unchanged, or they're the same, or something along the lines, or maybe they match something else. If we're talking about a null hypothesis about the slope, what would the null hypothesis be if we're talking about there's no change? What would the slope be of something that sort of is unchanged? Does that make sense? Basically, the slope is 0. The null hypothesis is the slope is 0. The alternative hypothesis is going to be either it's greater than 0, it's positive, it's less than 0, it's negative, or we don't know, right? We don't know. So the null hypothesis is going to be the slope is 0. Nice shot. The alternative is it's something other than 0. It's positive, it's negative, or we don't know. It's kind of like you're greater than, less than, and not equal to. You're not equal to, your I don't know would be your double the p-value kind of thing. So the test is just t equals beta sub 1 minus the hypothesized slope which is probably going to be 0 in most cases, divided by the standard error of the slope, your standard deviation. This is your claim. Probably it's going to be 0. All right, let's look at page 788, number 5. Beer and blood alcohol content. All right, so I'll tell you my college beer story. Don't get too excited, it's not all that exciting. So, when I went to college, I've always tried to be careful with overspending, stuff like that. I always spend everything I have, but I don't usually go into debt too much. So when I was in college, excuse me, my roommate was a computer science major. He was working as a programmer. He made good money. I had a good job. I was making pretty good money. We were both paying our own way. And it was really cool having Rick as a roommate because he always paid his bills. But even today, if Rick walked through this door, and walked into our room right now, I guarantee you'd all look at him and go, oh man, that's a nerd. That's like, he was the quintessential computer nerd, you know? So every now and then on Fridays or Saturdays, we'd go out and we'd go get a drink, you know, we'd go to a bar or something like that and see if there's any action. Well, here's the problem. You gotta kind of have money to go out to a bar because drinks are expensive. And we were both fairly cheap. I mean, we were paying our own way. So, like, we'd go with $6 in our pocket. That was our self-imposed limit. You know, you get to the bar at 8:30, you buy a mixed drink, that's $6 with a $1 tip. You drink it, and you're done by 9, maybe 9:15, okay? Because after the drink's gone, you're just kind of standing there like a fool. So, and this went on a couple, 3 times, and so I told Rick, I came up with this brilliant plan. I said, you know, if we started buying beer instead of mixed drinks, we could take advantage of a lower price. And maybe we could buy 2 beers, have a tip, and stretch it out to 9:45, maybe 10 o'clock, you know? All right? So the problem was neither one of us drank beer. I mean, neither one of us liked beer. So what was the solution to that? Well, we went and bought a 12-pack of beer. And we sat down for every day, and we drank a beer together every day until we could both stomach beer. And then we went out with our $6 and bought 2 beers and strung it out to, 9:30, 10 o'clock maybe. Okay, so, yeah, my beer drinking days as a college student were pretty limited and not very much. And I'm really thankful for that. So even now, I'm really not a beer guy. I'm not an alcohol guy either. I'll drink if somebody hands me something, and I might enjoy it, but I would never go to the fridge and grab one of the beers out of my fridge. I always have beer in the fridge in case somebody comes over and likes to drink beer, then maybe I'll drink one with them, but I'll never drink one just for me. It just isn't, it doesn't call to me, and I'm really happy about that. Now, cookies on the other hand, they call to me. If there are cookies in the cabinet, they're going to call to me until they're gone, and usually I'll sit down and I'll eat them until I'm going like, oh, I ate too many, or they're gone, right? That's just, that's the unfortunate reality of my addiction. So, conditions. So I can't have cookies around the house much. Conditions. That's what number 5 asks us about this. Well, hang on. I guess we better find out about the question, huh? Okay, so the question is, how well does the number of beers a person drinks predict his or her blood alcohol content, or BAC? 16 volunteers aged 21 or older with an initial BAC of 0 took part in a study to find out. Each volunteer drank a randomly assigned number of cans of beer. 30 minutes later, a police officer measured their BAC. A least squares regression analysis was performed on the data using X equals the number of beers and Y equals BAC. So they've given us a residual plot here, and it's asking us to check conditions. All right, so thinking about this, and they also give us a frequency table or a histogram of the residual values. Let's see if we meet our conditions. Is it linear? Do we have any evidence of a pattern in the residual plot? Hello, yes? No, yeah, no pattern. Right. So the residual shows no pattern. So I think we can say that's linear. Is it independent? Do you think it's reasonable to believe that each person who's volunteering for this is independent? I would think so. I would think that their blood alcohol content is independent, that the effects of alcohol on one person are not going to change the blood content of another person, right? Okay, so independent, yes. BAC of one participant will not affect another. Is it normal? Do we have any indication of normality? I'm going to say yeah, because our histogram of the residuals, while not perfectly normal, doesn't show any massive skew, nor does it have an outlier. It doesn't look like there's any outliers in there. So, yeah, the residual histogram is okay. Well, there might be some skew, but it's not crazy, right? And what was that other one? The one that I keep forgetting. The equal SD. On our residual plot, oh wait, this one here. Does it look like everything's scattered out pretty good? Like the distances from these points are pretty well equaled out with the distances of the points above it? Or does it look like one of them's crammed in there pretty tightly with more dots and the other one's spread out with less dots? I'm going to say that it looks to me like your separation, which is really what we're kind of looking at here, is good. So the distribution, I'm going to say the distribution on the residual indicates the standard deviations are equal. There might be a better way to state that. I actually don't recall that from our previous book at all, so that's a new condition for me. All right, and the last one, random. Was there something random about this? They couldn't randomly choose people, because if they did a random selection for people to drink beer, what if you get somebody who either doesn't drink or has a religious, maybe a religious or a philosophical this. It's random number of beers assigned. So wouldn't it be funny if you guys were the subjects of this, you guys were the volunteers, and I had a bin that had numbers from, say, 1 to 10, and I think it would be quite funny if Victoria got the one with 10, right? Come on, Victoria, slam them down. You need all 10 of those. This is for scientific reasons, right? The smallest person in the room gets the most. The one with the most beers, right? Okay. All right. So, where am I at here? Hiding this thing. So that's actually number 5, and there's only 2 problems. I know they're not written up there, but there's only 2 problems for you to do today. We're going to do 3 of them, 3 of the 5 that I assign here. Number 7 asks us, remember these guys? It's been a while since we've seen one of these. It's got all the goodies in there. Some of them are needed, some of them are not. Yeah, you hated those things? That's why I tried to give you a bunch last fall, so I knew they were coming back around. But it's been a while. So number 7 says, here's the computer output for the least squares regression line, or analysis anyway. And the first question is, what is the estimate for B sub naught? So A is going to be B sub naught. That's the y-intercept. Anybody have an idea which of these values is the y-intercept? What's that? What do you think? You used to know? Yeah. So the y-intercept is a constant. It doesn't change, right? So it's the constant coefficient. The constant coefficient. This is going to be your y-intercept, or your B sub naught. Okay. So this is the y-intercept, which in this problem is negative 0.012701. Right there. So if that's the y-intercept, B asks us, what's the slope? And why are they asking the best estimate? Well, because they're asking for beta, which is a parameter. So we're using a statistic to estimate a parameter. So which one's the slope? I'll give you a hint. It's in your coefficient column. It's the number you haven't used in your coefficient column.
0.0126.
No, that's standard error coefficient. This is your coefficient column.
0.179.
There you go. That's it. The number of beers, 0. So this is the slope. 0.017964. C asks us for the standard deviation, sigma. It's an estimate. Sigma is a parameter, so it's going to be a statistic. So what's our best estimate for standard deviation? Any thoughts? What's our statistic for standard deviation? What letter do we use? S, right? Or SX? There it is. Yeah, it's that. that's our best estimate. Now, these three guys are unbiased estimators. Unbiased estimators. And that's because they're unbiased because we've met all the conditions. So we think that they're good estimates for the population. And the last one is something I haven't talked about yet. Or wait, no, I take it back. The one that I'm going to add to it. What about the standard error of B1? This isn't really an estimate. This is the standard error of the slope. Standard error of the slope here. Yeah, what do you think?
Is it 0.0024?
It is. Yeah, good. It's this value here. So your slope, your y-intercept, your standard error coefficient is the 0.0024. Now I don't think you'll need this other stuff. The t-ratio and all that junk. I don't think that's going to be anything you're going to use. So I'm going to add one. E, what's the degrees of freedom? It's 14, right. But it's different than what we've done before. The degrees of freedom here is now no longer n minus 1, it's n minus 2. So that's 16 minus 2 is 14, right. So I didn't give you notes on that, n minus 2 now for this slope regression stuff. Okay, and let's look at number 9. I think I can just get it crammed in here on the bottom of the page. So number 9 says, where'd it go? Find the critical value for the 99% confidence interval for the slope of the true regression line, then calculate the confidence interval. And then interpret the interval and explain the meaning of the 99% confident in this context. So basically what I'm going to do is I'm going to combine all that, A, B, and C, and I'm just going to find the 99% confidence interval and give a response to it. So for number 9, I've got, I guess I need to get it where you can see it. I've got degrees of freedom is 9. I'm sorry, is 14. I know that it's a 99% confidence interval. I need a t value. I need t star. So I need to find t, and it's not in that table of stuff. There's like a t ratio thing, but that's not what we're looking for. So for t, I'm going to go to my t table here. I'm going to go to 99%, and I'm going to go up to 14, which gives me a value of 2.977. I kind of have to use the table here on this one. We've kind of gotten away from the tables a little bit, but you can't forget them. 2.977 is the t value. I have all the other values that I need here. Because the b sub naught and the b sub 1, that's what this actually is, the little b sub 1. So my confidence interval is going to be 0.017964 plus or minus 2.977 times the standard error of B, and that's going to be 0.0024. So we've got all the stuff. We just need to plug it into the calculator. minus first. So my first value, I get about 0.011. To about 0.025. So we are 99% confident. Move some stuff here so I can write. The true slope of the line of regression how about I say LSLR for least squares line of regression. It's a little shorter. Of blood alcohol content versus number of beers drunk, drank, drunken, I don't know. How about we just say number of beers is between 0.011 and 0.025. I probably should change the BAC and the number of beers. I probably have the order wrong there because the number of beers is your X and the BAC is your Y. Probably should, but I don't know that they would get that picky about that on the AP test. Okay. All right, so here's your assignment. Oops. Do numbers 11 and 15.